optimization. So number 5 says a printer needs to make a poster that will have a total area of 200 square inches and will have a 1-inch margin on the sides and a 2-inch margin on the top and a 1.5-inch margin on the bottom. I think I did this because this is what you need for like letters of rec in order to print on the letterhead. What dimensions of the poster will give the largest printed area? So as we sketch this out, whoops, we have a rectangle. And it says that it didn't really say like the print is 200 square inches, so I think the poster is going to be a total area of 200 square inches. It will have a 1-inch margin on the two sides. It will have a 2-inch margin along the top and a 1.5 along the bottom. Okay, so the whole poster, we'll call it X and Y, and we know that X times Y has to be a total of 200 square inches. Okay, that's what we call our secondary equation. And the reason that's our secondary equation is because it's not anything that we're trying to maximize or minimize, okay? So the question said, what dimensions of the poster will give the largest printed area? So the print is on the inside. So if I'm talking about the printed area, I want to find the dimension here and the dimension here. Okay? So I knew that it was X all the way across, so X was here. And what did I subtract out from both sides in order to get that inner width? Yeah, I subtracted out 2, right? 1 from both sides. You guys see that? So it's like it was X originally, and I'm cutting out 1, cutting out 1. Not really cutting it out, but this is gone and this is gone. So this distance right here will be X minus 2.
Each of those is X.
I don't know that each one's X. I know each one's 1. I think they're just 1 on the sides of the margins. Get it? All right. So now how about the other one? So the total height was Y, and what did I subtract from the top and the bottom, and what am I left with? So I subtracted a 1.5 and a 2, so I have Y minus 3.5, right? So this is going to be Y minus 3.5. Okay, and that creates the printed area. So our printed area is equal to X minus 2 times Y minus 3.5. Okay, and this could be different on a homework problem. Maybe I tell you the area of the print originally. So X times Y is the inner area, right? So you have to be very careful on these because a lot of people like do it one way and it's like really complicated if you do it the wrong way. Okay. So here I go. So I have my printed area as X minus 2 times Y minus 3.5. And I need to use the secondary equation to solve for either X or Y.
How'd you get the 3.5?
Because I have 2 and I have 1.5. So it's a total of 3.5. Right? Subtract the 2, subtract the 1.5. So I'm going to replace Y with what it's equal to. It's equal to 200 over X. So I'm going to replace there. So I'm going to have X minus 2 times 200 over X minus 3.5. And you can write that as 7 over 2 if you want to. Doesn't matter. So that's going to be A for area. So we're going to go ahead and FOIL out. And you don't have to. You could always like take the derivative now, but it's probably a little bit easier if you FOIL now instead of FOILing after the derivative. So when I do X times 200 over X, I get 200. My X times negative 3.5 is negative 3.5X. My negative 2 times 200 over X is negative 400 over X. So I'm going to write negative 400X to the negative 1. And my negative 2 times negative 3.5 is plus 7. Jake, you with me? Okay. So we get a total of 207 minus 3.5x minus 400x to the negative 1. So that's my area. Okay, we're trying to maximize this area. We want to find the largest printed area. So we're going to take the derivative. So I have A prime is equal to negative 3.5 plus 400x to the negative 2. So I took the derivative. Everybody with me? Okay. So simplify our derivative. So I have negative 3.5 plus 400 over x squared. So that's where I typically get my common denominators. I'm going to multiply by x squared over x squared. So I have A prime equals 400 minus 3.5x squared all over x squared. Okay. What did I just do with my calculator? Did someone take my calculator when I brought it up here? Oh, I put it on the tray. Very confusing. All right, so here we go. So let's go ahead and find it. So set each piece equal to 0. So I'm going to have my 400 minus 3.5 x squared equals 0. And then x squared equals 0 gives x equals 0, right? So that's the first critical value. So I'm going to do 400 divided by 3.5, and then I'm going to take the square root. So I get x equals plus or minus 10.690. And you guys remember in Algebra 2 and Pre-Calc when I taught you guys how to store? We're going to do that. So we're going to store it. So store is alpha A. Maybe it's something else since we have area in the problem, but that's fine. We'll go with A. All right, so we need to quickly show that this is creating a maximum area, so we do our number line. X really can't be anything less than 0, right? We have to have some kind of thickness to this paper. So we're going to start with 0. And then we have our 10.690. And then it can go up forever, but it's kind of weird that it goes up forever, so we'll leave it like that. So pick numbers that are close to your critical values. So like 10 and 11 would work. So if you plug in 10, the numerator is 400 minus 350, which is positive. The denominator is positive, so we get positive. And if I try 11, then it's a little bit bigger. 400 minus something bigger than what it was, so it's negative. So we go up and then down. So that does create a maximum. So you always need to do that quick check. Okay. All right, so what was the question? What did it ask for? What dimensions? So we have our x. So then go back in and find y. Y was equal to, what was it, 200 over x? 200 over x. So 200 over the 10.690, which we have stored. 18.708, exactly. So your dimensions was the 10.690 inches by 18.708 inches. So I'm using the inches mark. That's not second derivative or anything. Right. Okay, make sense? Did you guys try one like that on your homework yet? Have you gotten to it? Did you get it right? You think? Did it right? Okay. So someone got it wrong? We'll see. All right. This next one is like a classic calculus problem, a Norman window problem. Do you guys know what a Norman window is? Have you ever seen these? So it says a window is being built and the bottom is a rectangle and then the top is a semicircle. Okay, whoops. So, oh man, I've erased all of it. I want to draw my semicircle better. So this is called a Norman window. In case you're going to be an architect or anything, you need to know that fun fact. All right, so it says if there are 12 meters of framing materials, what must the dimensions of the window be to let in the most light? So the way that this works is this part right here is not really actually there. It's just all like cut like that. So we'll do like a little dotted line. Okay, so it's all like glass. And you're letting in the most light. What does that mean? Letting in the most light. Maximum what? Area, right? So we want the maximum area. All right, and there's 12 meters that go all the way around. So back when I first started teaching calculus, I kind of did this a hard way. And I've learned since then that I'm going to make it a little bit easier, okay? So the easiest way to do this problem is to let r be your radius of that semicircle. So then the bottom becomes 2r. Okay, and we don't know what the rest of this is, so we can have h and h on the two sides. But then what about the top? It is pi r. Good job, Julie. Do you guys see why it's pi r? What's the circumference of a circle? 2 pi r, but this is only half of it, right? So this is going to be pi r. So our secondary equation, the one that we're not trying to maximize, but is going to help us get it in a single variable, is that 2r plus h plus pi r plus h has to equal 12. So like going all the way around. You guys see all these pieces? Okay, that's going to allow us to solve for h. Okay, so if we want to do that now, we can. So we have 2r plus 2h plus pi r equals 12. We'd subtract our pi r over, we'd subtract our 2r over, and then we would divide everything by 2. So it's h equals, you can write it as 6 minus pi over 2r minus r if you want. Or you can leave it as 12 minus pi r minus 2r all over 2. So now let's talk about the equation that we're trying to maximize or minimize. Katie, with me? All right, so if I'm trying to maximize, I have a rectangle and I have a semicircle. So the rectangle has an area of 2r times h. And then the semicircle, right, a circle has an area of pi r squared. So it's going to be half of pi r squared, right? So it's going to be half of pi r squared, like that.
No, but why is the rectangle 2r h?
Yes. 2r times h.
Oh, okay. Just because of the 2 outside.
You might have been distracted by your cell phone there. I'm watching you. Eyes on you. I know. Roll your eyes. My Algebra 1 teacher, or Algebra 1 students, I made them put it on my desk when I catch them on their cell phones. So I won't do that to you guys. You're responsible enough to not to look at your phones and pay attention. All right, so here we go. So I have a equals, I'm going to replace the h. So I have 2r, and then h is 6 minus pi over 2, r minus r. There's a lot going on there, plus 1/2 pi r squared. So we're eventually going to take the derivative of this, but we want to clean it up as much as possible before we take the derivative, right? So we're going to distribute our 2r. So I get 12r minus pi r squared. Do you see it? So the 2's cancel. R times pi r is pi r squared. Minus 12r squared plus 1/2 pi r squared. So we can actually combine. Oh, did I mess something up? I think I'm good. Oh, instead of 12r squared, did I write 12? Oh, darn. Minus 2r squared, thank you. Man, you've just been on a roll lately, Charles. All right. Okay. So we can at least combine the negative pi r squared and the positive 1/2 pi r squared. Do you guys know what that will be? Combine them. Too much math. You're done. Checking out. Negative 1 plus 1/2 is what? Negative 1/2. So it's negative 1/2 pi r squared plus 2r squared.
Why is that? Why would it be negative 2 pi r?
Did I write? I'm messing up this r squared term once I get to it. Is that what you're saying?
No, what?
Is that a negative 2r squared?
Oh, wait, never mind.
All right, so we have 12r minus 1/2 pi r squared minus 2r squared. Do we have that? Okay. So now we're going to take the derivative. So our derivative is going to be a prime equals 12 minus, how about this part? The 1/2 pi is all just a number. So yeah, it becomes pi r, minus 4r, like that. Yeah?
Could we simplify an r out of this first?
You could like pull an r out, but then you'd have to do product rule, right? So
Yeah.
we try to keep it like a polynomial as much as possible. And so when we set equal to 0, we can subtract the 12 over, and we have negative pi r minus 4r. And this is where what Abby's saying, if you pull an r out, negative pi minus 4, lots of negatives. I could pull a negative out too, but that's fine. Let me get that. So now we can divide it over. So we end up getting negative 12 all over negative pi minus 4 is equal to r. So let's find what that is as a decimal, because no one wants to write that 18 times from now on. Yeah, you could make it divide by negative on the top and bottom. Yeah, that's how I'm putting it in my calculator actually. So r is equal to 1.680, and we store it. So we'll store it as b. I feel weird storing it as a because we talked about area, so we'll store it as b. All right, so now that you have that, the question is, what are the dimensions, right? So what must the dimensions of the window be to let in the most light? So that was the R value. So it's really like 2 R's down here. So like, how do you write the dimensions of a Norman window? It's not like length times width or anything. So what I tell my students to do is just draw a little sketch and I'll understand what's going on. So this is going to be R times 2 along the bottom. So 3.361. And then the height, I think it actually ends up being the same thing. So plug into your h equals 6 minus pi over 2 r minus r, and plug in that b value. And it equals 1.680. I guess it's the same as what r was. Okay, and that's it. Clearly not drawn to scale. So the Norman window looks more like this. But, you know, whatever. All right, do we understand that?
Where did the 3.361?
That came from, it was 2r originally, like in my drawing. Do you see how it's 2r on the bottom? So I just doubled it.
Oh, okay.
And then I guess I should put my units, right? These are meters. The big old window.
So is that the dimensions?
Yeah, those are the dimensions. So I was saying it's kind of hard to like write the dimensions of a Norman window. Like if you use the 2r along the bottom. Michaela? You could do the top if you want to as well, but it's kind of implied because of that inner radius. So it's okay if you don't put that part in. But if you did, it would be pi times r, so it would be 5 is that what you got? 5.279 meters. So you could do that part as well. All right, another one. Last one. So this last one kind of goes back to what we were talking about a long time ago with profit, revenue, cost. Okay, so it says recall profit is equal to revenue minus cost. Remember I talked about like a lemonade stand? The amount of money that's in the jar is your revenue. You take out what you owe your mom if you're a good kid. Usually you don't take out what you owe your mom, do you? And that ends up being your profit. So the average cost is also the total cost divided by the number of items that you sold. Okay, so it says suppose a factory has a revenue function of r of x equals 300x and a cost of x cubed minus 6x squared plus 15x, where x represents the number of items produced in a day. So what is the average cost for 20 items? Do you guys remember how I wrote average cost? I like saying it. C bar. You guys remember that? That's how we read it, C bar. So we take our total cost, which was our x cubed, minus 6x squared plus 15x, and we divide by the number of items, and our number of items is x. So we're finding the average cost for 20 items, so we're going to plug in 20. So we're going to have 20 cubed minus 6 times 20 squared plus 15 times 20. That would be the total cost for 20 items, and we divide by the number of items.
Can you pull up that x?
Sure, you could, and then reduce it down. Yep. Did you guys get it? 5,900? So in a single day, make $5,900. Did I do that right? Oh wait, divide by 20. Did I forget my divide by 20? Ooh, that'd be a lot of money though. I was like, ooh, that's a good one. All right, is it 5,900 divided by 20? So 295? Yeah. All right, so what is the cost of producing the 20th item? So do you guys remember how to find the cost of producing the 20th item? I know this has been a while. We can't spend every single day of calculus reviewing everything we learned before. It would never work. So you got to remember some of these things. So we know the total cost of producing 20 items, but what about just producing the 20th item?
Divide by 20.
No. That's the average cost of the 20 items, but maybe it's like cheaper as you're producing more and more and more, right? You've invested, you've got this like machine that's helping you. The cost of the first 20 minus the cost of the first 19, right? That would be the cost of the 20th item. Does that make sense? So the cost of the first 20 items is 5,900. We just found that. And then the cost of the first 19, plug in 19. Anybody have it?
Plug in 19 to what?
Into the cost function. So that was 4,978. So we get a total of $922. Ooh, that's a lot. Is that right? So it's more expensive to create the 20th than the first one, I guess.
Why is the cost for 19 items more than the cost for 21?
The cost for 19 is less, right? 4,978. Isn't that right?
Oh,
Okay. So it says, is there a production level that maximizes the profit, and if so, what is it? So our profit is equal to our revenue minus our cost. So our revenue was 300x, so we must be selling things for $300. Does that make sense? 300 times the number you sell. And then minus the cost function, so I'm going to put parentheses. So minus x cubed minus 6x squared plus 15x. So my profit equation is 300x minus x cubed plus 6x squared minus 15x. So I'm guessing if you're selling the items for $300 and the cost of the 20th item is costing you $922, you don't want to sell 20 items, right?
yeah, where did the
Seems like a lot.
Oh wait, out of it. Okay, alright.
Yeah. So now we take the derivative. So I have 300 minus 3x squared plus 12x minus 15. And we want to set that equal to 0. So negative 3x squared plus 12x minus 15. No, wait. Minus, yeah. So let's combine those. So minus 15 and then plus 300. So plus 285. Yeah. All right. So we could do a quadratic formula. I'll let you plug it into your calculator as y1, and you can find the x-intercepts.
Why didn't you do the derivative?
I did do the derivative. You see it?
Derivative of 3x.
I went from here to here, right?
And then how did you take away?
So I set it equal to 0. So mine's not showing up. I'm guessing it's on the right side somewhere, right? So I'm going to make my x max go out to like 20. See if it crosses. It's somewhere in there. All right, so do second trace 0. Make it on the left side and the right side. Anybody have it? No? Am I the only one who used my calculator? Natalie's using her calculator. Did you get it, Natalie?
I have the calculator. 11.950.
Exactly. 11.950. Now, why does the negative one not matter?
Oh, is that what it was?
Yeah, x is like the number of items you're producing, right? So,
Destroying what you have.
yeah, we don't want to destroy what we have. That's the opposite of a factory, destroying things. So if we create around 12 items, then we're good. Wonder what you're producing. I have no idea. It's like these profit ones are like totally made up. Yeah.
Does it make sense that would actually happen? That it costs
Yeah, because maybe like it costs more to bring a certain amount of materials in, or you don't have enough, so you're paying like a extra shipping charge for materials, or maybe you're trying to like only use your people for a certain number of hours per day, but then now you're paying overtime. You know, like there's lots of situations where it would be too much. Yeah, kind of weird. That's your econ lesson for the day. Thank you. Channeling my inner Maggie Dean. All right, so let's stop there.